嗨红，我已经把你设为了联席主持人了。
OK，
嗯，需要什么操作的话，可以直接在上面操作就可以。
嗯。
我们再等5分钟吧，现在
好的。
可能稍微有点早，这个
啊，
大家还没有根据昨天的经验，一般到现在正是人进来的时候。
现在国内开会是一般还是 remote 吗？还是这个已经开始像以前正常那样开会了？
我们现在是就是除了网上，我们现在这些人，就是我们还有一个街道有一个教室，因为这是 colloquium，在教室那边可能有 graduate 所有的 graduate student 在那个
哦
教室里面，他们在看屏幕。
哦这样。哦
对，
哦
嗯，
嗯。
哎，周洋早上好，刘红早上好，刘红是晚上好，晚上好，
哎，林毅你好。
哎，
没看到你的那个，没看到你的。
我没开视频，在办
哦
公室，
这样的。
我刚到办公室，
哦，
你在家里面吗？
我在家里。
啊，你的背景是实景图吗？还是用的那个
是
插入的
实景图啊，就
背景？
在家里。
啊，
在家里一个小房间里，对。
啊，书房里面。怎么样啊？现在大家都很关心啊，这个美国现在这个波士顿这边是不是也比较严重啊？整个疫情现在。
波士顿还好吧，这个比其他地方可能好一点，但是总的来说美国都比较严重。然后现在就等着疫苗了。
所以是不是基本上都不去校园呢？现在？
哦，早就没去校园了，这个半年都没去过校园了。
哦，也不让进是吧？
校园可以进，就你如果要，但是要首先去测了之后，然后才能进。哎，
哦，
就是要登
那
记。
小孩上学的情况呢？现在也都不
小孩上
上学了吧？
学，小孩上学就是分2部分，有一部分是就可以，就是你可以选择是在家上，还有另外一个可能性就是一半一半，去1个星期，然后在家待1个星期。
那现在其实做父母都不放心啊，他去学校园其实也还是有感觉，现在有这种风险呢，就是。
对，就是，但是学校还好，他这个一个教室这个做的比较细呗，大家都戴口罩，然后
哦
还好。对
哦，是
对。
希望这个赶快这个疫苗出来，大家就都安全了。差不多时间到了啊，就是。OK，
对，时间刚到，我们好，现在是40，对，我们另外还有一个教室，那我们就开始吧。Good morning, everyone. Welcome to the second day of our workshop. Today we are really happy to have Professor Hong Liu from MIT to give us a colloquium I should mention there's another big classroom where might be nearly 100 students, graduate students were there. They are sitting there to also catch this colloquium. Before Professor Liu starts, let me briefly introduce Professor Hong Liu. Professor Hong Liu is a theoretical physicist at MIT. He received a bachelor in 1993 from University of Science and Technology of China, and a PhD in 1997 from Case Western Reserve University. He was a postdoctoral fellow at Imperial College and the New High Energy Theory Center of Rutgers University before joining the faculty at MIT in 2003. He was Alfred Sloan Fellow, an outstanding junior investigator of Department of Energy, a Simmons Fellow, and Guggenheim Fellow. He has been an editor of JHAP since 2010. Among many famous achievements of Professor Hong Liu, let me briefly mention a few of them. So he was among the first to use string theory method to study properties of quark-gluon plasma created at Brookhaven National Library, and was among the first to point Let me continue. I'm really sorry. Let me continue. He was among the first to point out possible deep connections between black hole physics and certain electronic properties of high temperature superconductors. He also shed new light on superfluid turbulence with the help of black holes. So recently, using insight from string theory, he developed a complete formulation of fluctuating hydrodynamics, which I guess he will introduce to us today. Personally, I maybe I should mention Professor Liu is really, in particular for Chinese young generations. I think we all get inspiration from him by his research works and his lectures. With that, let's warmly welcome Professor Liu. Yes,
Okay, yeah, thanks a lot, Yang, for this nice introduction. And it's a great pleasure to give the colloquium today. So today we'll talk about some aspect of hydrodynamics in exotic quantum matter. Fluid phenomena are really ubiquitous in our life. So it's in our body, and we travel, use it, and all kinds of disaster. And also it governs the dynamics inside the Earth, inside the sun, the galaxy formation, and the cosmological evolutions, etc. So hydrodynamics, of course, has a very long history. It can be dated back to Archimedes, say around 2000 BC, and many great scientists like Da Vinci, Newton, Euler, Bernoulli, etc., have made a great discovery regarding hydrodynamics. And the basic idea of hydrodynamics is what is called the fluid approximation. It approximates a continuum, say it approximates your system by a continuum of fluid elements. So each of which is considered to be a macroscopic object in local equilibrium. Okay, so in this fluid approximation, each point in your fluid should be considered as say as a local equilibrium, and should be considered governed by local thermodynamics. And the basic variables of fluid dynamics in so-called Euler formulation, for example, is given by the local density, local temperature, and the local velocity flows. And then what you do is you express your energy and momentum in terms of these phenological variables. And then hydrodynamic equations are just energy plus momentum conservations. And also, if you have a conserved other conserved quantities, then you also have continuity equation. Okay, so it's extremely simple, just conservation equations, but it's been extremely powerful. And the hydrodynamics also has made some unexpected entries in 21st century physics. So let me quickly give you a few examples. So the first example is the quark-gluon plasma. So at room temperature, because of the strong action, quarks and gluons are always confined inside the so-called colorless hadrons, say like protons, neutrons, and pions, etc. But if you heat such system to very high temperature, and then hadrons actually will melt. And then quarks and the gluons will be deconfined, and then they can move free around, they form a liquid phase. And so this is so-called the quark-gluon plasma. So quark-gluon plasma has been conjectured since early days of QCD in early 1970s. But finally, around 2000, it was realized in the lab through the heavy ion collisions. So here is the basic idea of heavy ion collisions. So imagine you collide two nuclei. Say, for example, here is the net. They each have 208 nucleons. So you collide them at very high energy. So when they collide together, and then some of those nucleons and will strongly interact with each other. And those interactions will turn the kinetic energy of those nucleons into the thermal energies. And then if the initial kinetic energy is big enough, and then you can thermalize the system, and then to raise the temperature above the so-called deconfinement temperature, and then the quarks and gluon will be liberated. So form this quark-gluon plasma. And so, of course, the whole system is really in the highly dynamical state. So this quark-gluon plasma, after it's formed, quickly expands because of the two nuclei, they move apart very quickly. And then when you say, when the quark-gluon plasma expands, just like an expanding universe, its temperature decreases, and eventually will drop below the deconfinement temperature again. And then the quark-gluon plasma will hadronize. And then, so what do you detect? Yeah, in your detector, just thousands and tens of thousands of particles, hadronic particles formed by the hadronization of the quark-gluon plasma. And of course, the challenge of the experimental program is to, by looking at all those particle trajectories and try to deduce the properties of the quark-gluon plasma formed in the collisions. So the quark-gluon plasma formed during such kind of heavy ion collisions are extremely tiny. It's a small droplet. Because its size just essentially determined by the size of the nucleus themselves. Say for example, it's say about 10 to the minus 14 meter, and the lifetime extremely short. Say it's about 10 to the minus 23 seconds, and the temperature is about 10 to the 12 K. So as I mentioned, that the experimental challenge is to deduce the properties of the quark-gluon plasma by measure all the particles you observe in your detectors. And then, so properties of the quark-gluon plasma just encoded in the correlations of those detected particles, okay? And it turns out remarkably, that the evolution of the quark-gluon plasma can be explained. Yeah, it turns out that the correlation of particles can be explained very well if one assumes, if one makes a very simple assumption that the evolution of the quark-gluon plasma after its creation follow hydrodynamics. Okay, and just with this simple assumption, and then with a few tunable parameters, and then you can explain experimental data extremely well. And so this tells you actually the GOP, the quark-gluon plasma really behaves like a fluid. In particular, it's not just like a fluid, it actually behaves like a perfect fluid. It's like a fluid with almost without viscosity. So yeah, so yeah, normally yeah, fluid one of the very important properties of the fluid is its viscosity, and what we call ideal fluids or perfect fluid are those fluids with viscosity is almost zero. And the quark-gluon plasma just behaves like that. And my second example is graphene. So graphene was discovered around 2004, and was given Nobel Prize, I think maybe around 2010. And so but normally we can see the electrons, say, in the metal. Here is the heuristic picture. Say you have like impurities, and then electrons move in the metal ballistically, and occasionally interact with the impurities. That's how you get resistance. But the graphene also, it's a conductor. It conducts electricity very well. But it turns out in graphene, the electrons actually behaves like a fluid, rather than like ballistic particles. Here is another cartoon picture for the electrons in the graphene. Here it just fancy picture to show its fluid-like behavior. Turns out that there's a very simple experiment to tell whether electrons in the graphene behaves like fluid or like ballistic particles. So here is a very simple setup. So imagine you have a slab of graphene. Okay, so this is the square here. And now imagine you put some voltage difference at 2 points between the upper side and the lower side. Okay, so you have source and drain. And so if electrons in the graphene behaves, say, ballistically, and then you will just measure then you see some resistance, and the electron will just flow from the source to the drain, and then you can just measure some resistance from your voltage differences. But if the electrons in the graphene behaves like fluid, and then as I mentioned, the fluid has viscosity, and then you can generate this kind of vortex that configuration. So it means that the electrons not only will flow down from the source to the drain, it can also flow back, okay, form this kind of vortex kind of configurations. So this kind of backflow, so when you measure the current and the voltage difference, and this kind of backflow then just behave like you actually have lactive resistance, okay, because the resistance, the positive resistance with like the ordinary flow. So if you have a backflow, just like you have lactive resistance. And this was the prediction made by my colleague Levitov and Fokovich around February 2016. And soon after, very quickly around the same time, in March 2016, the experiment which reported the discovery of lactive local resistance was precisely discovered. Yeah, was precisely found in the graphene, and they precisely through the in this Manchester group they just did they just did this experiment and then precisely see this kind of lactive local resistance. Okay, so this is strong evidence that actually electrons in the graphene actually behaves like fluid. So my third example is Archer code Fermi gases. Okay, so here is an example of a confined cigar-shaped cloud of fermionic lithium atoms. Okay, so this color coding is the blue means this the density is very low, and this yellow the density is very high. So those atoms are confined by some external potential at the beginning, by some external potential in this cigar kind of shape, and the temperature is extremely low and 10 to the minus 9K. So now the question is whether the question is now suppose we release the potential. Okay, just now remove the potential. When you remove the potential, then the atoms in this gas then will just fly around. Okay, so now the question is how will this gas behave? Will it behave like a liquid or behave like a gas? Okay, so that's the question. Okay, and so that's the experiment done by this Thomas Schaeffer's group around 2002. No, not. Yeah, I think it's John Thomas group. Yeah, anyway, so the basic idea is that now you release the potential. So if this behaves like a liquid, and we know the liquids have a balanced pressure throughout the liquid itself, and then because the cigar shape have shorter distance in the horizontal direction than the vertical direction, and it means you have larger pressure gradients in the horizontal direction. And the larger pressure gradient means that when you remove the potential, then the particle in the horizontal direction will move faster. Okay, and then you will see this kind of a thing called elliptic flow, that a particle moves faster in the horizontal direction than in the vertical direction. But suppose this was not like a fluid, suppose this is like a gas, and the particle can just move around freely, there's no collective motion. And then they will move in all directions uniformly, and very quickly this just becomes isotropic. Okay, and so the experiment shows actually such kind of Archer code atomic gases really exhibit collective flows and also governed by hydrodynamics and indicating a viscous fluid. So now I have talked about 3 examples. So they are all extreme. Yeah. So these are 3 types of exotic quantum matter. Okay. And so these are, and this type of these 3 type of systems, they have very different temperature and interactions. Okay. So for the quark-gluon plasma, you have strong interactions, and at the 10 to the 12K, so this is essentially the highest temperature one can achieve so far. And then and for the graphene, the main interactions are just Coulomb interaction between the electrons, and it's at the room temperature. And for these Archer code atoms, and the interaction just atomic interactions among the atoms, and at extremely low temperature. So essentially the lowest temperature you can achieve on Earth. So the question is why somehow the hydrodynamics is so effective in describe such quantum matter with diverse interactions and so wide range of temperatures. Okay, so actually there's a very simple reason behind it. So yeah, the reason. So let's imagine, say, you have a system which is in equilibrium. Okay, now let's imagine you have some long wave disturbance around the equilibrium. Okay, say by long wavelength disturbance, we mean that the wavelength of disturbance is much larger than the mean free path, which I indicated here by right line. And you can imagine this is, say, this is a curve for some physical quantity, and the horizontal axis is some spatial direction, and the vertical axis is the magnitude of this quantity. The equilibrium will be, say, this quantity just constant. Okay, and now we have a long wavelength fluctuation. And the subsequent evolution of such kind of a disturbance depends very much on whether this quantity you perturb is actually a conserved quantity or non-conserved quantity. So if it's a non-conserved quantity, then you can relax locally. And so at every point in space, they can just go back to equilibrium, okay? Essentially locally through local collisions. Okay, then the typical relaxation time would be just the mean free path, the mean free time, okay? So your typical mean free time. And so a mean free time is typically microscopic, so happens extremely fast. But if you have a conserved quantity, so by definition, conserved quantity cannot be destroyed, okay? So they cannot relax locally. So the only way for conserved quantity to go back to equilibrium is for the access to go to the deficit region, okay? Can only through the transport, and for this conserved quantity to go from this access region to the deficit region. But now, if you imagine that the wavelength is very, very big, and then of course the time of the transport will also become much, much bigger. Okay. In particular, if you take the wavelengths go to infinity, and then the relaxation time actually go to infinity. And then that means that if we are interested in physics at the time scale and the length scale much larger than the mean free path and the mean free time, and only dynamics of the conserved quantity are relevant. Okay, so all other details are washed out by interactions. So all non-conserved quantities, they just locally relaxed in a very short time scale, and this non-time scale physics are just controlled by conserved quantities. And as I mentioned before, that the hydrodynamics is precisely the theory of conserved quantity, just energy momentum conservation. Okay. And so hydrodynamics is really a universal theory, say for non-equivalent dynamics of generic many body system at sufficiently long distance and times. So, and the key is that the distance and the time must be much greater than the mean free path and the mean free time. Okay. So now we can come back to these three examples to deduce. Now we understand why hydrodynamics apply to them, because somehow for hydrodynamics to apply, the mean free path for this system have to be sufficiently short. Okay, so we can turn this around. That's the fact that the hydrodynamics apply to them. It means that the mean free path for each interaction must much be smaller than the size of the system, okay, or than the size we observe the system. So for example, for quark plasma, as we mentioned earlier, quark plasma is extremely tiny. So this is a droplet of 10 to the minus 14 meters. But that means the QCD mean free path at this kind of at the temperature scale probed by experiment should be actually much, much smaller, even at this 10 to the minus 14 meter. Okay, so that's actually a strong indication that QCD at this temperature scale is still strongly coupled. Okay. And similarly, the graphene you used to do the experiment is also pretty tiny, and that again you can turn around to argue that the electrons in the graphene, they actually have to be strongly coupled to each other in order for hydrodynamic approximation to apply. And the same thing with these ultra-cold atoms. Okay. So now we can just use hydrodynamics actually to define a class, say strongly quantum, to define a class of quantum matter which we call strongly interacting quantum liquids. Means that at the observable, say, distance scale and time scale, they are actually controlled by hydrodynamics. Good. So this is a quick review, say, of some of the applications of hydrodynamics. So, but despite the long and this glorious history of hydrodynamics, there's still important defects, say, with the formulation of hydrodynamics. So hydrodynamics, as we mentioned, are formulated as equation motions. They're just conservation equations, okay? So by definition, if you are formulated as equation motion, and they cannot capture fluctuations. But of course, we know the fluctuations are always there. And so there exist phenomenological fixes to add the fluctuations by hand. But those kind of phenomenological fixes you add by hand, they can work, say, if you are near equilibrium. But when you are far from equilibrium, and then they don't apply. Okay. But as I mentioned, actually, statistical fluctuations are everywhere. And actually, in many physical contexts, they actually play a very important role. So also, if you go to sufficiently low temperature, and actually quantum fluctuations can also be important. So now let me just give you a couple of examples where the hydrodynamic fluctuations actually plays a key role. So the first example is this famous more than 100-year-old problem called the Rayleigh-Ballard problem. So the setup is very simple. We observe every day in our kitchen. Suppose you have a tank of water, and then you heat the water near the bottom of the tank. Okay, so you have some, so there's one temperature in the bottom, and then above is the top of the tank is the room temperature. So now if the temperature difference between the top and the bottom is small, and then the stationary state of the system is just there's no macroscopic motion of the fluid, you will just see a temperature gradient, say from the bottom to the top. Okay. But now, if suppose you increase the temperature in the heating temperature in the bottom and increase and then the gradient will increase, then at certain critical temperature difference between the top and the bottom, and then the curve action will start. Okay, then now there's a macroscopic motion of fluids in the tank. Okay, and the transition between them is actually like a phase transition, and the transition actually is induced by hydrodynamic fluctuations. And so this is what we normally call the line equilibrium phase transition. Okay. And another important application of hydrodynamic fluctuation is in the search for the QCD critical points, which is actually an experimental program which is actually going on right now at Brookhaven. So this is the phase diagram for the QCD. There are lots of things in this diagram which you don't need to know. So let me just say a few simple things. So the vertical axis is the temperature, and the horizontal axis is the baryon chemical potential, or the baryon density. So at the very small baryon density means that you have equal, say, equal amount of quarks and antiquark. Say if the system is almost neutral, then the transition between the hydronic gas to a quark-gluon plasma is actually a smooth crossover. And that's indeed what was obtained, what was observed at Brookhaven and LHC. Okay. But there are many theoretical supports that when you go to sufficiently large density, okay, so suppose you have many more quarks than antiquarks, say you have a sufficiently large chemical baryon chemical potential, and then at a certain point, this transition becomes first order. And then just from simple, then there must be a critical point somewhere in this phase diagram, okay. And you can, and actually there's a simple argument that this is actually behaves like the, essentially like water vapor critical points. Anyway, so the search, to try to find this critical point is a huge experimental challenge. And in particular, to find this critical point, one have to rely on large fluctuations around the critical point. Yeah, because by definition, the critical points are distinguished by the very large fluctuation around it. Okay. So now if you can create the quark-gluon plasma, say with parameters around this critical point, then you should be able to observe large fluctuations in such quark-gluon plasma. And then in particular, you need the fluctuating hydrodynamics to be able to describe the evolution of such kind of quark-gluon plasma. Okay, yeah, good. So the last example is is turbulence. Okay, so of course turbulence is also ubiquitous in life. It's everywhere.
So
so there's a simple, yeah.
Ask a question about the QCD critical point.
Okay.
Is there a CFT description at that point?
Sorry?
Is there a CFT at the QCD critical point?
Is there a CMT description you're saying?
CFT. Conformal field theory.
Oh, yeah. This is just a three-dimensional Ising model.
Oh, I see. Thank you.
Yeah. This is like a three-dimensional. Yeah, just purely from the critical, its equivalent properties is described by three-dimensional Ising model, but then its dynamical critical behavior is described by a so-called model H. Anyway, so this would be the order parameter, say, of QCD, and then coupled to hydrodynamics. Yeah.
Okay, thank you.
Yeah, the effective series, no, yeah. Anyway, so a lot of places which thermal fluctuation can potentially play a role, which is actually an outstanding open question right now, is whether the thermal fluctuation can play a role in the turbulence. Okay. So there's a very simple reasoning. There's a very simple argument given by David Real actually in late 1970s. He argued that actually thermal fluctuation should play a very important role in turbulence. And his argument is as follows. Say, imagine, because turbulence is highly nonlinear and chaotic behavior. And as we know, for highly chaotic system, if you have some small initial disturbance, and then that disturbance will quickly be exponentially magnified and grow and into macroscopic disturbance. And now imagine the system have some kind of small thermal fluctuation. And then he deduced that the thermal fluctuation should also be magnified very quickly. And then he estimated the time scale and the length scale for such kind of thermal fluctuation to be magnified. And then he concluded actually such time scale are comparable to the typical scale of turbulence. Okay, yeah, typical macroscopic scale of turbulence. But this is just very crude. This is a very crude heuristic argument. So it's still an open question whether thermal fluctuation actually plays a very important role in turbulence or not. And if it does, then that will have very important implications. Say, for example, for weather forecast, because say for the forecast of a hurricane, etc. And because that the thermal fluctuation will significantly limit our ability to predict the turbulent behavior. Anyway, so to answer those questions from first principle, one need the formulation of fluctuating hydrodynamics in far from equilibrium situations. And so in particular, in order to capture fluctuations, you actually need the formulation based on action principle. It's just not enough to have equation motions. Okay. And the searching for action principle for dissipative hydrodynamics has been a long-standing problem in mathematical physics. Dating back at least to Hergelos, who wrote down an idea of fluid action in 1911. And of course, many people have looked at this problem, including the Nanda-Lifshitz. The Nanda-Lifshitz had proposed a version, say, of the fluctuating hydrodynamics by putting stochastic terms, say, to turn the hydrodynamic equation into a stochastic equation, which, as I mentioned earlier, only works for a linear equilibrium. And during the last decade, there have also been renewed interest in this problem from many different areas, say including cosmological applications, also just from condensed matter applications, also just from the string theory, the holographic duality, etc. Okay. So a few years ago, with my former students Glorioso and Crossley, we formulated. We proposed a complete formulation of this fluctuating hydrodynamics, which also we later developed together with Ping-Gao. And here are some of the papers which here are some original papers. We also had a review about 2 years ago. And and the formulation actually used the ideas of quantum field theory and the insight from gravity and string theory. Okay. So now let me just briefly tell you how we solve this problem. The basic idea behind the formulation. So the framework we use to address this question is called effective field theory. So the idea of effective field theory is very simple. So let's imagine we have a full path integral, say, of some quantum many-body system. Okay. Of course, this is extremely hard. We don't know. Except for a very small number of integral systems, we don't know how to do this path integral. Okay. But the key in but the important idea is that for most purpose, we don't actually need to solve this theory exactly, because we are only interested in the low energy physics. So we are only interested in the macroscopic physics. And for that purpose, we only need to identify what are the important low energy degrees of freedom. Okay. And then we can just imagine, say, suppose we can identify the relevant low energy degrees of freedom, and now let's imagine we integrate out the rest. Okay. And then we will get effective action for this low energy degrees of freedom, and then that will just capture all the important physics. And in particular, this now the system is greatly simplified because we only need to focus on a very small number of important low energy degrees of freedom. Okay. And so this SE, we just get this low energy effective action. And of course, this kind of integrating out is not possible by direct computation. What one can do is just to identify the symmetries, and the constraints should be satisfied by this effective action, and then we just write down the most general theory consistent with the symmetries. Okay, and we just write down the most general theory consistent with the symmetries, and then we determine, say, the finite number of parameters in such series, say, using experiments. Okay, so this has been an extremely powerful paradigm in many areas of physics, including almost all condensed matter physics and almost all particle physics, and also many applications in cosmology, etc. Okay. And we should be able to, as I emphasized earlier, the hydrodynamics should also be considered as some kind of universal low energy effective theory, and then we should be able to formulate hydrodynamics this way. Okay, we should be able to formulate an action principle for hydrodynamics based on this kind of ideas. Okay, so here are some basic challenges. So the first is that of course, hydrodynamics is dissipative, and then there's a standard law that the dissipative systems actually don't have an action formulation. Okay, and the simple example is just the friction, say, from your high school physics, and it's generally not known. At least you were normally told that such a equation does not have action formulation. And then another challenge is what are the right dynamical variables one should use to formulate such kind of fluctuating hydrodynamics. So as I mentioned before, the standard variables are phenomenological variables, say the density, temperature, velocity, etc. And with a little bit, say, trial and error, you could see that those variables are actually extremely awkward to use if you want to write down action principle. So this is a little bit similar to the situation of the Maxwell equation. So the Maxwell equation are written in terms of electric and magnetic fields. But if you want to use electric and magnetic field to formulate the action principle for electrodynamics, that actually does not work. You have to introduce the vector potential. Okay, you have to introduce the potential. So so those variables are analog, say, of those electric and magnetic fields. So here the challenge is we need to find the analog of the potentials for those variables. Okay. And then the last, he said after you identify the variable, so after you find ways to incorporate dissipation, and then you have to incorporate the symmetry. Then you have to impose the symmetries. And again, this aspect is not very simple as in ordinary applications, because the question is what kind of symmetries actually define a fluid. Okay. Somehow the symmetry must be able to distinguish a fluid from a solid or from liquid crystal, etc. Okay. Let me just tell you how we actually address those problems. Okay. So it turns out, so it's a little bit, the idea is not very intuitive. It turns out, in order to write down an action principle for hydrodynamics, say in flat space, say in a classical statistical system, actually it helps to go to quantum mechanics, to start with quantum mechanics, and to actually go to curved space-time. Okay, so now let me explain how we do that. So it turns out that the issue of dissipation is actually laterally resolved by quantum mechanics. Now let's imagine we just say we have a quantum mechanical problem in the non-equilibrium state. Okay, and that's what we'll be interested in when we formulate the hydrodynamics. And so in quantum mechanics, the non-equilibrium formulation, you use a density operator to characterize the system, initial density operator, then you involve it. And the density operator involved by this U and U dagger, okay, and then that's corresponding to two paths. So two path integrals. So one corresponding to U, which going forward in time, and the one corresponding to U dagger, which going backward in time. But now if you want to calculate some observables, so you take the trace, and then essentially you can just close, just identify one end point. So here we identify the final point of these two contour, and then corresponding to take the trace. And then this defines what's called the closed time time curve, which you're going forward in time from minus infinity to plus infinity, and then go back to the minus infinity. Okay. So this sometimes called closed time path or the Schwinger-Kadich contour. So it turns out, so if you want to describe a non-equilibrium dynamics of your quantum system, then you have to formulate your theory on such kind of contour. Okay. And in particular, if you want to go to describe the low-energy physics, and then you have to develop effective field theory for system on such a closed time path. Okay. And this formulation on the closed time path is different from our usual formulation, because this involves going forward in time and then backward in time. So essentially, this contains two copies of your original system. Okay, so one copy going forward and one copy going backwards. So corresponding to actually double the number of degrees freedom of your original system. Okay, if you just count the t go to minus infinity plus infinity, and then that corresponding double the number of degrees freedom of your system. So it turns out that this double number of degrees freedom is extremely powerful. And once you do that, and then the dissipative effect, and also retardation effect just automatically incorporated in your effective field theory. So you don't have to do anything. You don't have to do anything special. So one example is the Brownian motion. Say the Brownian motion can just formulate on such a kind of closed time path, and then you treat this heavy particle in the Brownian motion say as your low energy liquid freedom, and then you integrate out the bath around it, and then you get the quantum effective action, and then you can take the classical limits. And in the classical limits, and then you get the action principle for Langevin equation. So somehow this quantum mechanical formulation is more natural. And then if you want to go to classical, just take the classical limits. Okay. And now let's go to the question of the dynamic variable. So one challenge of, say, formulating these hydrodynamics, which are based on conservation equations using action principle, is the following. When we say the hydrodynamic is the conservation equation. So conservation equation by definition is just equations. They're not action, okay? And so seems like you are stuck already at your starting point because because these are conserved quantity, and the conserved quantity are defined by the conservation equations. Okay. So now the key issue is we want to so in order to identify these reversal variables associated with energy momentum conservation, somehow we have to rephrase the energy momentum conservation in terms of some kind of symmetry principle. Okay, rephrase in terms of some symmetry principle. It turned out actually there's a simple mathematical trick, is to put the system actually in the curved space-time. So as we know from GR, from general relativity, if your system satisfies the energy momentum conservation, okay, and then when you put such system in the curved space-time, and then that system is actually diffeomorphism invariant. Okay, so this that's how we couple say a quantum field theory to gravity. Okay, because of the energy moment conservation, and then the system is diffeomorphism invariant. So that means that now you can rephrase the statement of energy momentum conservation in terms of the statement about the diffeomorphism invariance. And the statement about diffeomorphism invariance is a symmetry principle. Okay, it's a symmetry statement. And the symmetry statement, then you can do it at the action level. Okay. So yeah, so diffeomorphism also means just invariant on the any coordinate transformation. So now this, from our usual field theory trick, and now this suggests a natural variable, which are automatically be diffeomorphism invariant, is that if you promote your space-time coordinates into actually dynamical variables. Okay, so now you just integrate over all possible diffeomorphisms. You just integrate over all possible coordinate transformations. And then of course, when you integrate over all possible coordinate transformations, then that's invariant under any coordinate transformation. Okay, so now we identify such kind of coordinate transformation. Identify the coordinate transformation as a dynamic variable, and that's our hydrodynamic variable. Okay, so that's the basic idea. And now you can show, if you do so, and then the equation motion of this dynamical coordinate transformation precisely equivalent to energy momentum conservation. Okay, and now you can just write down the action for this x mu, just use the symmetry principle. Okay, but here there's something weird going on. So x mu is your original space-time coordinates, and now you promote it into a dynamical variable. And this dynamical variable should be the function of something else. So you need to have a reference space-time, and so that you can consider the arbitrary coordinate transformation as a dynamical variable. And then you have to, and that means that you need to introduce a new auxiliary space-time, a fixed reference space-time, so that you can talk about the dynamical coordinate transformation. Okay. So at first sight, this this new space-time, this new reference space-time, somehow you have to introduce in order to promote your coordinate in dynamical variable. Seems very weird. Okay, but actually there's a very simple physical interpretation. Okay, so let me write also remember we have two contours as emphasized earlier. So there are two copies of dynamical variables. Okay, and their functions of this reference space-time, and sigma I can be some spatial coordinate, and sigma 0 is some time for this reference space-time. Anyway, so here here is your topic variable. And it turns out that this has a very simple interpretation, just as the generalization of the Lagrange description of a fluid. So now let me first remind you what's the Lagrange description of a fluid. So as I mentioned, that you can label a fluid by looking at the, say, some space-time point, and then look at the say the local temperature, local density, and the velocity at that space-time point. Okay, this is so-called Euler description. But there's another equivalent description of a fluid, so-called the Lagrange description. Is that you follow the motion of a fluid element. Okay, just here there's a right line here. We follow the motion of a fluid element, and so you are in the core moving. You can see the core moving frame of the fluid element, and then we can label this fluid element by some label. Say let's call sigma I. Then the motion, then the fluid motion in space-time, then just corresponding to, say, xi as a function of this labeling and the t. Okay, you fix sigma I, fix the label, and then this xit then just describe the trajectory of your fluid element in space-time. So now we see this just precisely, now the sigma I and the sigma 0 here can be precisely interpreted as the label the fluid elements, and the sigma 0 just as the internal time associated with each fluid element. And now, so we refer this as a fluid space-time, which corresponding to the labels of fluids and its time. And then you have physical space-time, and then this dynamical variable just describe the mapping, say, from your fluid elements to your physical space-time. Okay, so if you fix sigma I, then the trajectory of x1 and x2 just describe the trajectory of this fluid particle in your space-time. So now, essentially through this fancy technique, say, of going to curved space-time, etc. So what we recovered essentially just a Lagrange description of the fluids. Okay. And now we can talk about what symmetries define a fluid, etc. And so again, this becomes natural when we interpret this sigma I as the labels of fluid elements. So for fixed, say, time, then you should be able to relabel your fluid elements. Okay, you should be able to relabel your fluid element. So, when you take sigma I to some arbitrary sigma I prime, your theory should be invariant. And similarly, if you fix the fluid element itself, and if you look at the trajectory of that fluid element, and that trajectory should be time reparametrization invariant. So anyway, so yeah, but those properties depend on sensitivity depend on actually this is a fluid, because if you have a solid, and then you don't have such a relabeling. Because for the solid, each solid element has an equivalent position. You cannot arbitrarily relabel them. Okay. And so these are kind of symmetries which are distinguish which distinguish the fluid. And there are also some other constraints from unitarity, from somehow this is come from a quantum mechanical system, etc. And turns out actually they are constrained from quantum unitarity, which actually survive in the classical limits. Okay. And then finally, as we mentioned, that one important feature of a fluid is that there should be local physical equilibrium. And now we need to impose this physical equilibrium again as some kind of symmetry. It turns out that there's a somewhat non-intuitive, but a very simple way to impose it is actually as some kind of Z2 symmetry, and which we call dynamical KMX symmetry, which then you can use it to impose the macroscopic time reversal and the local equilibrium. Anyway, so with those inputs, and then you can just write down a statistical field theory, and then which fully recover the standard hydrodynamics, say as equation motion. But also treat the statistical and quantum hydrodynamic fluctuations systematically. So one benefit, say, of such an action formalism it's actually, it gives rise to a new formulation of the second law of thermodynamics. And one can show actually, yeah, so one can actually combine these unitarity constraints and this dynamical KMS symmetry, and one find actually the combination of them leads to a local current. So this dynamical KMS symmetry is a Z2 symmetry. So we know the Moser theorem. So if you have a U1 symmetry, then that leads to a conserved current and a conserved charge, etc. But here, this dynamical KMS symmetry, which imposes the local equilibrium, is only a Z2 symmetry. It turns out this Z2 symmetry does not lead to a conserved current. But when it combines with the unitarity constraint, actually give you a current whose charge actually is monotonic, okay, does not decrease with time. And so, so this we identify with the second law of thermodynamics. And the charge for this local current then just identified as entropy. And in particular, this is more than just give you the second law to show that the entropy difference is non-increasing, but actually give you a combination to work out explicitly the explicit form of the entropy production in the universal way. Okay, yeah. Anyway, so another thing which happening is that turns out that this action also have many other kind of theoretical properties, so including that this thing can always be supersymmetrized, so emergent supersymmetry, etc. So I'm really running out of time, and so let me just be quick here. And also this framework is very general and can be generalized to other continuous media, such as solid and liquid crystal, quasi-crystal, etc. And there have been lots of recent developments. Okay, so for the last couple of minutes, let me just very quickly mention a recent application which we use it to describe quantum scrambling and the quantum chaos. So chaotic phenomena are ubiquitous in nature, and in particular, classical chaos has been highly developed since 1970s. But much still to be understood in quantum many-body system. So chaos in quantum many-body systems still far from being understood, but it's still believed to be very important. So classical chaos now is essentially as the foundation of the statistical physics. Okay, say the thermalization, transport, etc., can all be attributed to the chaotic behavior. So it's tempting to think that the chaos will play a similar role, say, in quantum many-body system. And so there actually have been intense recent studies of quantum many-body chaos using this so-called the out-of-time ordered correlation function. So this is a long story. I will not go into there. So the bottom line is that it turned out one can use this hydrodynamics formulation to formulate the quantum hydrodynamic action, okay, to describe this, a so-called maximally chaotic system. And in particular, one can identify a so-called chaos mode, which effectively captures the dynamics of the chaos. Whose dynamics give rise to the chaotic dynamics. It turns out this chaos mode can be identified with actually hydrodynamic mode associated with energy conservation. Okay, and from that, then we can actually equate an effective theory of chaos with a quantum hydrodynamic theory, because the chaos mode is just corresponding to energy conservation. Okay, and then we can just from energy conservation we can just write down quantum hydro theory. And then this will give you a number of implications and predictions, including explaining connections between energy diffusion constants and the quantum chaos observed in the literature, and also predict the new manifestation of quantum chaos, we call the pole skipping. And also there are surprising connections between quantum chaos. These surprising connections between quantum chaos and hydrodynamics is still remain mysterious, but but anyway, but seems like very interesting connections. So now let me just summarize. Say hydrodynamics plays an important role in characterizing various exotic quantum matter. So at the beginning, it may seem surprising that hydrodynamics is so powerful, but once you understand its universal nature, and actually you can actually turn it around, use it as a reversal definition of strongly coupled quantum liquids. And also now we have a first principle formulation of hydrodynamics, which can incorporate statistical and quantum fluctuations. And then I described unexpected application to maximal quantum chaos. Yes, I will stop here. Thank you. Any questions?
Hello, can you hear me?
Thank you.
Yeah,
for the
yeah, I hear you.
Yeah, I have maybe a brief question. About the statement of KMS symmetry plus unitarity eventually leading to the second law, meaning the increase of the entropy. I'm wondering, like, how is the direction of time is determined then? How do we really determine the direction of time? Because there has to be some kind of anomalous property, right? Or some kind of symmetry.
Right. That's an extremely good question. That's an extremely good question. It turns out, so mathematically it's the following. So mathematically, you see, here is the so when you formulate this D2 symmetry, mathematically when you formulate this D2 symmetry, it turns out there's a choice of sign. Okay, so there's a choice of sign which you can choose in this dynamical KMS symmetry. And so one sign, these two, so this dynamical entropy implies that the entropy is always monotonic. So either monotonic increase or decrease. And then whether it's increase or decrease, then depend on a choice of a sign in this D2 symmetry. So this D2 symmetry can be formulated with either sign that give rise to consistent theory. But only one sign of them then corresponding to actually entropy increase. Okay, so somehow this arrow of time is incorporated in the choice of the sign in this dynamical KMS symmetry, and also it is the same sign which guarantees that, say, the series causal. Say, for example, the retarded Green function, the pole are all in the lower half plane rather than in the upper half plane, etc. Yeah.
All right, thank you. Very amazing.
I have a question.
Yeah.
You can hear me?
Yes.
Okay. Yeah. My question is about the definition of entropy. I think, here, my question is whether your definition of entropy as an integral is diffeomorphic invariant or not.
This is no longer diffeomorphic invariant. It's because the So here when we talk about this entropy, we have already choose fixed geometry. So when you when we formulate the system, we put in the curved space time, etc., and then integrate over all possible coordinates. But when you do the actual formulation of the hydrodynamics, in the end, you just set the background to be flat space. to be flat space. And that was just a mathematical trick to help you identify the dynamic variable. And so in the end, everything is still in flat space. And yeah, so this is just the, but of course you can generalize to curved space-time, but then will be a fixed curved space-time. And because the fluid just move in some kind of fixed space-time. Yeah.
Okay, so my understanding of your answer is that finally you will take your curved space-time background as a flat space-time. Is that right?
That's right. That's right. Yeah. That curved space-time was just a trick in intermediate steps. Yeah.
Yeah. Okay. That's all right. You know, in Landau Lifshitz book, you know, to compute generally the energy momentum tensor of a system, they use this trick, right?
That's right. Yeah.
Yeah. Okay.
Yeah.
Same trick.
Yeah. Same trick. Precisely related. Yeah. Precisely related. Just precisely that the energy momentum tensor can be considered as a response to a curved space-time, to a deformation of curved space-time, and then that you can formulate the conservation equation in terms of the symmetry. Yeah.
Yeah. So here you mentioned that emergent entropy as a Noether chart. So what's the symmetry which is related to the Noether charge? That's the Z2 symmetry?
Yeah, that's the Z2 symmetry. Yeah.
Okay. So Z2 symmetry, however, is broken, right?
No, Z2 symmetry is not broken. So Z2 symmetry is the exact symmetry of the action.
However, you answer a previous question about you know, the direction of the closed path loop. So I thought, yeah.
Oh, right. Yeah. Let me clarify. Yeah. I think my answer maybe. What I meant is the following: is that when you write down this Z2 symmetry, when you write it down, there's a choice of sign. There's a choice of say suppose let's formulate this Z2 symmetry to be say x plus y or x minus y. Okay. So x plus or minus y both work, but then we just choose one of the sign.
However, the question is whether if you change another sign, would you also change the sign of the entropy or?
Yeah, that's right. No, you don't change the sign of the entropy, but you do change the direction of the entropy.
The direction of entropy. Then that means entropy increase would become entropy decrease?
That's right. Yeah.
Okay. However, on your slides, you have it greater than 0. Does that fix the sign of the Z2 symmetry?
Yeah, just say this corresponding to the choice of sign, which you so this corresponding to the choice of one sign. Yeah.
Okay. Can you specify your choice?
Yeah, I didn't include the explicitly. I should have included the explicit expression here. If I included the explicit expression, then it's clear where does that sign come from. Somehow I don't have that equation here. But it's a freedom which you can somehow, when you formulate this Z2 symmetry, there's a Z2 freedom, you can formulate this Z2 symmetry. Yeah.
Okay. Yeah. Actually, I would like to see the
Yeah.
explicit
And that leads to
things.
freedom.
I think it's very interesting.
Yeah. Yeah, and that lead to freedom can be understood exactly as the actually I forgot the detail. I need to remind them actually myself, but we actually showed in the paper that D2 freedom is exactly the same as the D2 freedom in the formulation of the Boltzmann's H theorem. So when Boltzmann formulated his H theorem, there's also Z2 freedom, which he needs to choose, and it's the same freedom. Yeah.
Okay. Okay. Thank you.
Mm-hmm.
Could you send me a reference of your
Sure.
paper?
Sure. Yeah.
Okay. Thank you.
Yeah.
Any other questions?
Yeah, I have a question. So for the coordinate description that you labeled by x mu, does that x mu necessarily have the same dimension with like sigma coordinates?
Yeah, they do. They have the same dimension. Yeah.
Okay. So, yeah.
They are all just number of space-time dimension. Yeah.
Okay. So this is not quite related to like the holographic description of a strongly interacting system. Like, yeah, because there you also have a diffeomorphism invariant description of the fluid. So I thought there might be some connection, but
no, it's not directly related to holographic description. And in the intermediate step, we have got some inspirations from the holographic description, but in the final formulation, you don't have to talk anything about the holographic formulation.
Yeah. I see. Thank you.
So I have a question about regarding the entropy as a Noether current of the Z2 symmetry. So usually only continuous symmetry will lead to a Noether current. So I'm confused why discrete symmetry can give you a Noether current.
Right. Yeah. You see. Yeah. So he actually works pretty non-trivially. So normally when you have if you have a U1 symmetry, then you have a conserved current. But now imagine you have a Z2 symmetry, and now you can try to just follow the Lother procedure, try to write down a current. And then you find actually there's ambiguity in defining the currents. Then there are two things. First, the ambiguity in defining the currents, and the second thing is that the current is just not conserved. You can define some current, but that current is not conserved. But it turns out the system has very strong this unitarity constraint. And now if you combine this unitarity constraint, which I didn't write down, with the two symmetry, and then actually that can be used to fix the form of the current, and then this leads to this monotonicity. Yeah.
Thank you.
Last question regarding this point. So basically, the proof of the Noether theorem is a classical field theory, right? So
yeah.
Here you said only Z2 is not enough. You have to resort to this unitarity constraint. But unitarity per se, it's a quantum mechanical concept. So I'm confused why when you prove some Noether-like theorem, you have to resort to quantum mechanics.
Yeah, good.
To the classical field theory, you know.
Right, yeah. So the basic idea is the following: is that here you so here you start with a quantum system, then you formulate this quantum system on this kind of closed time path, and now when you write down the effective field theory, then that effective field theory should satisfy some constraints. Because it comes from a quantum mechanical system. Okay, so again, that constraint is some constraint on the action principle. It's not, it's just some constraint on the action principle. It turns out that those constraints actually survives in the classical limit.
Okay, you are working on quantum effective action.
Sorry?
you are working on quantum effective action. I mean, this generator of the 1PI diagrams. So
no,
I'm confused.
it's not the,
okay.
It's not the 1PI diagram, it's just the standard Wilsonian kind of effective action.
But it's quantum effective action, not classical effective action.
Yeah, at the beginning it's quantum mechanical, just h bar on 0. And then once you write down that effective action, and then you can take h bar goes to 0. It turns out that when you take h bar goes to 0, those constraints from quantum unitarity actually do not go away. They actually survive in the classical limit.
So what's the physical picture of unitarity in the classical theory? Is something like some kind of conservation of what? Probability, but it's quantum mechanics. So it must not be probability, right? It's something else.
Yeah, so it's more like the following. So it's more like, say, if your classical system comes from the classical limit of a quantum mechanics, then actually that classical system is more constrained than some arbitrary classical system you can write down. Okay. So I believe this kind of constraint, you may be able to formulate it using some kind of Hamiltonian, classical Hamiltonian kind of language. Yeah, but we haven't tried to do that. Yeah.
But normally speaking, the unitarity in quantum mechanics is very simple. Usually, if you have a Hermitian Hamiltonian, you automatically have this unitarity.
That's right. That's right. Yeah. So here you have a little bit. Yeah. So in that example, if you just take the standard example and say the unitarity of quantum mechanics, when you go to the classical limit, it's more like somehow your Hamiltonian essentially have nice properties. Just say it's more like for a conservative system.
Here you have dissipation.
So here, because you are formulated on this closed time path, so there's a richer set of constraints.
Okay, but I'm a little bit worried about you have this dissipation. You have, the theory not be necessarily be the Hermitian, right? The Hamiltonian could be non-Hermitian. Is that right?
No. Here, yeah, indeed. But now you have, so here you formulate on these two copies of the system. You formulate on this closed time path, so that your constraint actually is more complicated and more intricate, rather than just Hamiltonian is a Hermitian or not. Hamiltonian is always Hermitian, but now there are additional constraints.
Okay, and can you say a few words about how do you take the h bar goes to zero limit? Since you didn't mention in detail, so how do you go back to the classical limit in your work?
Yeah, so h bar goes to zero limit is the same as, say, imagine you have a quantum many body system. Okay, so let's imagine you have a set of operators, and then they just calculate the correlation functions of those operators in your quantum theory. And now let's consider the classical limit of those correlation functions. And in the classical limit, those correlation functions should reduce to correlation functions in your classical system formulated on the phase space. Okay, and this is the exact same limit. And the key of this limit is that this limit throw away quantum fluctuation, but still keeps the classical fluctuation, still keeps the statistical fluctuation.
Okay.
Yeah, let me just mention one more sentence. Normally, say, when you have a path integral, a quantum mechanical path integral, then we say when you take the classical limit, and then that path integral become the saddle point approximation, become classical motion, right?
Right.
But then here's something else going on. Here, because we are looking at the quantum many-body system, now when you take the h bar goes to 0, actually you don't go to the saddle point. When you take h bar goes to 0, you still get the path integral. And the remaining path integral actually incorporate the statistical fluctuations.
Okay. So in theory, basically you keep a finite temperature, right?
Yeah, that's right. Yeah.
Okay, thanks.
Oh, can I ask a quick question?
Sure.
Yes. I'm still a bit confused about how we can have unitarity at the same time as having a direction of time. And then the second thing is how do we see that this conserved charge is in fact the entropy as we know it?
Yeah.
The thermodynamic.
Right. So unitarity is not incompatible with the direction of time, because the direction of time can come from asymmetry, say, of the boundary conditions. Can come from asymmetry of boundary conditions. And so here, if you really trace it, actually I forgot the detail, but I did mention earlier that here there's also asymmetry. Yeah, as I mentioned, somehow the sign here, the direction of time comes from somehow the Z2 freedom to choose the sign, formulate this Z2 symmetry, and then you can trace that freedom. Where does that Z2 freedom come from? And then you find actually that's related to you treat your initial condition and the final condition asymmetrically. And so that's actually the same kind of asymmetry in the Boltzmann's H theorem. Yeah.
I see.
Yeah, it's related to somehow the time boundary, some kind of asymmetry between the initial and the final boundary condition. Yeah.
I see.
Right. Yeah. Sorry. Then you have a question regarding the entropy.
Right. How it's not obvious here how we see that it is the same entropy as we know it in the context of thermodynamics.
Right. Good. Yeah, indeed. So here you did not know a priori, because here we just try to construct some current, and you just follow the Noether procedure, and then you try to construct the current, and then you find the current, and you find this S0, and then what you find is that the integral of this zero. So this equation is general, applies to both equilibrium and non-equilibrium situation. But now if you now reduce to the equilibrium situation, and then you can just write down, and then you find that this just coincides with the standard definition of the entropy.
Oh, I see.
Yeah.
I see. Oh, thanks.
Yeah, but this gives you a generalization, say, of entropy production, even in the far from equilibrium situation. Yeah.
I see. Thank you.
Mm-hmm.
Any further questions? Any other questions? If not, let's thank Professor Hongyu again.
Yeah, thank you. Mm-hmm.
Okay, our next talk will start from 10:30.
Okay, so I will stop sharing the screen. Yeah. Mm-hmm. Okay, thank you.
Thank you.
Hi, Yang.
Hi.
Could I try to share the screen to see if it works?
Please.
Yeah, I have two names here. One is my monitor, the other is my device. So yeah,
okay.
Maybe you need to set the Pingal's tablet as a co-host. I'm not sure.
Yes. Pingal设为主持人。免洗Pingal's tablet。
Oh, yeah. Okay, fair. And
Give me 1 minute. My internet is really unstable.
okay.
All right, I'm back. Hi, Yeqing.
Hi.
So you are going to chair the next talk.
Yes, in 1 minute, right?
Mm-hmm.
Okay, let's start the next session. Welcome back, everyone. So the next talk, the next speaker will be Ping Gao from MIT. He will be talking about matrix model of JT gravity with dynamic end-of-world brain. Please welcome the speaker.
Okay, thank you, everyone. Thanks for inviting me to this interesting conference at Fudan University. Today, I'm going to talk about work in progress with Daniel Jeffries and David Kochmeyer. The title is Matrix Model of JT Gravity with the Dynamic End-of-World Brain. In this talk, I will have 5 parts. The first is to discuss the classical solution and the phase space with JT gravity, of JT gravity with a boundary brane. Then we solve out, after solving out the phase space, we'll have a canonical quantization of it. Then from the canonical quantization, we will see the structure. Then we'll describe how to find the dual matrix model based on the famous duality between pure JT gravity and double scaling matrix model, which is proposed by Shanker and Stanford last year. The fourth part, I will basically tell you the result of the duality, especially the density of state. Though I said it's checking duality, but because of the time being, I will only compute it from one side and tell you that from the other side it is matched. The last part, I will give you some discussions and also mention the work I'm still the questions we are still working on. Hopefully will be resolved in a few weeks. Okay, so let me start. First, let me quickly introduce what is JT gravity. JT gravity is quantum gravity of in 2 dimensions. So it contains Einstein term, which is a constant phi now over 4G Newton. Then contains the dynamical part of in 2D. The first term is phi times r plus 2. This term basically tells that the metric in 2 dimensions is ADS2. Then there is a Gibbons-Hawking-like term in the ADS boundary, and there is another term which is action on the brane. Okay, so the picture would be this, where we have the right boundary to be ADS, the left boundary to be the brane, which is a sort of word line living in this 2-dimensional space. So the U is the local proper time on the ADS boundary, and the V is the local proper time on the brane. Okay, so here I just plot a Cauchy size. This 2D JT gravity can be regarded as like a dimensional reduced theory from higher dimension. For example, if you start with 3D gravity and reduce the transverse circular direction, you will get this JT gravity plus this Einstein term. So this term, this phi now, basically describes the extremal. Sorry, yeah. If it is a higher dimension of 3D extremal black hole, then this phi now corresponds to the horizon area, the extremal black hole horizon area, and this phi corresponds to the variation of the transverse area. So this describes a near extremal geometry. Here kappa is 1 over 8 pi g Newton. Okay, so with this action, the first thing we would like to do is take the variation and find the equation motion. As I said, the first term will give us, r plus 2 equal to 0. And if you vary to the metric, you will also get this term in the bulk. Okay. On the other hand, because we have 2 boundary terms, and after the variation of the action, you will get the boundary variation to be this, which implies that you should have this guy equal to 0 or the variation part to be 0. And we also have another variation, which is the variation of phi on the boundary. That will give us the term like this, where C and D are different numbers on different boundaries. For example, on the brane, the C equal to 0 and the D equal to mu, and on ADS boundary, C equal to 1 and D equal to 0. So this is the boundary condition from the variation principle. On ADS boundary, it is conventionally to choose that the metric and the dilaton to be fixed, just like the Dirichlet boundary condition. So we fix the metric and fix the phi dilaton. So this gives us these two. So this is okay. On the other hand, we'll choose on the brane the opposite choice of the boundary condition. Okay. Oops. Oh, the other boundary condition, we'll choose this term and this, show this and that. The point is that we allow the metric to be varying along the brane, and we also allow the dilaton value to vary on the brane. But on the other hand, we have to fix the normal derivative of dilaton and also the extrinsic curvature to be 0. And here I need to mention there's a recent paper by Go, Eliseu, Krusov, and Yang. They discussed various types of boundary conditions of this underworld brane and discussed their properties in the Euclidean spacetime. In this work, we'll have a different point of view to discuss those features. And we will only focus on special boundary condition, which is here. Yeah. Now we can solve this equation motion. It's well known that this is the global patch of the ADS2. And this metric has the SO2,1 gauge symmetry. This symmetry is global, but in this theory, we'll regard it as a global gauge symmetry, which means we'll have a then this gauge group has 3 parameters, and we're going to fix and treat all the solutions along the gauge orbit to be equivalent. So we can use the 2 parameters to fix the dilaton solution to be this, where we should require this phi h parameter to be positive. The physical region is phi plus phi now to be positive. As I mentioned before, the phi corresponding to the transverse area from higher dimensional gravity. So it must be positive because we must have a positive area of some transverse sphere. So because of this constraint, and you look at this solution, you immediately get that the T must be bounded from minus pi over 2 to pi over 2 if it is asymptotic to ADS boundary. So this is the plot of the geometry of the solution of the geometry. The horizontal is sigma, and this is T. And there are 4 wiggle lines corresponding to the singularity, which means the phi plus phi now to 0. And there are 2 ADS boundaries, and there are 2 horizons. Okay, on the horizon, the dilaton value is fixed to be a constant, which is the phi h here. So it should be positive. Okay, so on the ADS boundary, to be more precise, we'll fix the boundary condition to be this, and phi to be this. And we'll take an epsilon go to 0 limit. Now we can solve this boundary condition because we already know, we already have the solution. So we plug in this boundary condition, and we got this solution. Notice that this is the black hole solution, because the U takes all the value in real numbers, and the left hand side is still bounded, right? So this corresponding to the asymptotic ADS boundary, okay, from minus pi over 2 to pi over 2, in which the U go from minus infinity to positive infinity, plus infinity. Here the U now, which is important later, it is the 0 point of the boundary time. Okay. And then on the underworld brane, because we choose a boundary condition to be so, there is this is one piece of boundary condition which says that the extrinsic curvature is 0. This means that the underworld brane is a geodesic, whose general solution is this. Okay. Because this underworld brane must be time-like, so this restricts the R to be bounded to be this, from -1 to 1. Now, recall that the SL2,1 symmetry has 3 parameters. We already used the 2 parameters to fix the Dilaton solution, and the last one we can use to set the theta equal to 0. So we'll get a we'll get the solution sigma equal to arc cosine R times cosine T. Let's take this solution into another boundary condition, which says, oh, sorry, this is a mistake. I should say this is mu. Yeah, the normal derivative of the phi is mu. Here is mu. Okay, so we can use this and solve the parameter R of this geodesic. Okay, so you see that after solving the whole question, the whole problem, the end-of-war brain's dynamics is completely determined by the parameter mu and the Dilaton horizon value phi h. Okay. Now let's talk about the phase space. Because we already solved the equation, the classical solution, and we know from classical mechanics, the phase space is equivalent to the space of solutions. In other words, we can use the free parameters in the solution as the coordinate of phase space. Okay, so now let's recall what the parameters we have. We have the phi h, and we also have the 0 point time on boundary, which is u now. Okay, so this is a 2-dimensional phase space. But to have a better understanding, we'll use a different variable to parameterize this phase space. So basically, we'll use a method proposed by Harlow and Jeffries. We will use the geodesic length of a more geometrical quantity to parameterize the phase space. To be more precise, we'll take the geodesic that connecting the brain orthogonally all the way to the boundary and end up with u equal to 0 point on the ADS boundary, okay? And this length L will be one parameter of the phase space. Indeed, this is divergent because ADS because of ADS space has a divergence of the metric near boundary. So this is a bare length which is divergent. So we'll regularize it by subtract 2 phi b over epsilon. So the phi b over epsilon is actually the boundary value of the Dilaton. So this is the convention we choose to regularize the length. After some algebra, you can get this result, and where the W is the phi h over phi b times u0. Okay. Now, if we require the solution to be valid for all the phi h greater than 0, this basically requires that the mu should be non-negative. Okay, so basically we'll take the mu equal to non-negative throughout the whole work, throughout whole talk. Okay. This basically means the mass of the word line, the mass of the endobrain is positive. Okay. Now the Hamiltonian ADS space is the same as the ADM energy, so we can just compute use the standard formula. It goes to phi h squared over 2 phi b. Okay. Notice that there is no Hamiltonian from the brain because we can compute the stress tensor on the brain, but it is actually proportional to the normal derivative of a Dilaton minus mu, which is the boundary condition that we choose to be 0. So we just choose the boundary condition such that there is no Hamiltonian from the brain. Okay, this makes things more simple. Makes things simpler. Now we know that for the classical mechanics, the next important thing is to understand to find out symplectic 2 form. The standard canonical 2 form should be del u0 wedge del h, right? Because Hamiltonian means the conjugate to the time translation on the ADS boundary, and we can use a variable of W to write in the form of this. Notice that we already have the solution of the L, okay? So we can use this formula to rewrite the symplectic 2 form to be del L wedge del P. Now we can solve the form of P such that and find out it is this form. Okay, using this, we can notice that the Hamiltonian is phi h squared over 2 phi b. Okay, so we can use this P to solve out the Hamiltonian, right? So we get the Hamiltonian to be you know, kinetic term and a potential term. This potential is actually the conventional Morse potential. Morse potential is very well known potential because it's widely used to study molecule physics. And here is the plot of the potential. If the mu is positive, it is exponential decay. But if mu is negative, there is a well and decay to 0. Okay, we will only consider the mu to be positive case because we do not want the bounded state, which is the case for mu to be negative, right? But that is the interest of the molecule physics. The immediate result of this Morse potential is that large L asymptotically we will get free quantum mechanics. And this corresponds to a repulsive force between the end-of-world brane and the ADS boundary, right? Because you can consider the end-of-world brane has a scattering in a space-time, and initially it is a large L, but because bounded by, is bounced back by this exponential wall, it will be bounced back to infinity again. Okay, great. So now we already have the classical solution. The next step is to get the quantization, right? The quantization is very straightforward, and it's just canonical quantization. We take the P to be minus I partial L. Now to solve the Schrödinger equation, this is just you know, undergrad problem, and we got this differential equation, and the result is the energy eigenwave function is this, equal to this guy. This is a Whittaker function. The z equal to 4 times E2 minus L, and the eta is a normalization. Normalization give us by, you know, gamma function and sinh function. Here the k is related to the Hamiltonian in this form. Basically, you can understand the k as the asymptotic momentum of the scattering problem in this Morse potential. Okay, great. Now this normalization is defined such that it is a delta function normalized. Great. Then we can compute the propagator. Okay, this is the next thing where we you know, the most natural thing we can compute next. Okay. Also, we can compute the partition function, which is simply take the 2L parameter of a variable to be the same and integrate over all the L. It turns out this guy is divergent. Okay, it's divergent. Why this is divergent? Well, this is because, you know, for the large L, it is asymptotically flat, so it has, you know, infinite space of the L variable. So the partition function should be divergent. But we can rewrite this partition function in a more useful form, which is this guy. Okay, let me explain more details. This is the integration of B, okay, from 0 to infinity. The first kernel is Z trumpet. Okay, why this is Z trumpet? This is the Euclidean path integral of a trumpet shape of the geometry like this, where the right end of the trumpet has ADS boundary condition, and the local proper length is beta. On the other end, it is a geodesic with length b. Okay, so in this very famous paper by Sass, Sinker, and Stanford, they compute the partition function of this trumpet, and its form is this. Okay, it is finite and it has this form. So this is the path integral, Euclidean path integral of this guy. Now the second term is E2 minus mu B over 2 sinh B over 2, which we regarded as the measure of end over work brane in the Euclidean path integral. What does it mean? It means that, you know, the Lorentzian, okay, in Lorentzian picture, we have end over brane. So this is the ADS, this is the brane. Okay, so when we compute the partition function, this corresponds to, you know, you have a trumpet shape, right? You just do the Euclidean path integral of a trumpet that should correspond to the partition function. So the first term corresponded to this trumpet partition function, but we have the end work brane which is glued to this geodesic boundary. So we will regard the second term as the measure of this gluing. Okay, so this is the physical picture is very clear that we glue a measure, we call it MB, to a geometry which will compute as the partition function of this end work brane system. Okay. Now let me later I'll use more in more places of this formulas, but now let me give you remarks. First, the partition function is divergent for small b. As we can see here, the Z trumpet is normal for b equal to. Sure, sure.
So that one you just explained that partition function, how it different, how it's different from the single disk.
Oh yeah. Oh, that's a good question. From a single disk is the one that there is no end work brane. So there is no end work brane, that is a single disk. But if you consider the system like one end is ADS, the other end is end work brane, you should have a trumpet geometry, right? So they are computing different contributions, right? Or later you will see, like, if you consider the partition function of the whole system with and without end work brane, you have to consider, the disk plus one end work brane and two end work brane and even more loops of end work brane and sum all of them together. Okay, that is something I will show you later.
Yeah. It's effectively just a half of the two boundary without end of work brane. You're just doing a quotient of that without any singularity in the middle.
Sorry, can you say your question again?
Is what you are computing the same as only a half of the configuration with only two ADS boundaries?
Yes, exactly. Yeah, you can say so. Like we cut the two trumpet into half and we glue the measure. Yeah, that's the same thing. Yeah.
This is because you just choose the Bernoulli tension sort of equals to 0 or something like that.
Yes. The point, the whole derivation here, I'm showing that from the canonical quantization, we got the partition function, which can be rewritten as the kernel integrate over integrate against a measure. So this is So from this formula, you can interpret it in the way that I just said.
I see. Thank you.
Yeah. Okay, great. So any other question? Okay. So for this formula, the Z trumpet is regular when b equal to 0, but this formula is divergent when b equal to 0. So this is a divergence. Okay. But B, what is B? B is the loop length of the end work brane in the bulk. Okay. So this means that to have a finite result, we have to require some bulk UV regulator or some UV completion of the bulk gravity to make it finite. On the other hand, as I just said, the divergence from the propagator point of view or the boundary point of view is from large L limit. Okay. So in the boundary, we have a large L to give this divergence, which corresponds to energy go to 0. Okay, because it's free. So this basically means that interesting connection, that is a boundary IR data correspond to the bulk UV data. Okay, so this is IR UV connection. which is actually quite normal in ADS-FT, right? Because for example, in the bulk you have like a strong coupling string limit may correspond to the IR phase of the boundary. Yeah, sorry, I said wrong. Yeah, the highly stringy coupling in the bulk may correspond to like IR non-trivial phase in the boundary. Okay. Now the third remark I want to make is that from the Euclidean path integral, one can consider a marked end-over-brane, which may give a factor of B, which means so this is a pure Euclidean point of view that you consider there's a mark on the end-over-brane. So you have one more modulus-based volume, which is B in this integral, and that will make integration finite. This is considered in this paper. But the question is, its Lorentz interpretation is not clear to me. Okay, but then on the other hand, I want to, in other words, that I think this divergence is quite physical and strongly rely on the bulk UV physics. Okay, so let me discuss the dual matrix model due to this gravity story. In the paper by Sad, Schenker, and Sanford, they show that the pure JT gravity is due to a matrix model in double scaling limit. The key equality is the following. Okay, the left-hand side is pure JT Euclidean path integral. I call it Z JT with the beta 1 to beta n, where the beta 1, beta n corresponding to n ADS boundaries. Okay, with local proper length beta 1 to beta n. Okay, then you can use whatever smooth geometry with whatever genus to connect all of those boundaries and sum all of them together. The right hand side is the expectation value of the trace E2 beta 1h to trace E2 minus beta nh in a matrix model in double scaling limit. To be precise, this guy is computed in this way, where we integrate all the n by n Hermitian matrix H, and with this specific potential. Okay. The double scaling limit is important. The physical meaning of the double scaling limit is that we take the n to infinity, but we still zoom into the corner of the spectrum, okay, and such that the density of eigenvalues is fixed at the order of E2S naught, okay, which means it is fixed in a finite number, okay. So this is the this is the full spectrum, and we only zoom into the corner to get this guy. Okay, this is double scaling limit. The connected piece, of course, can be dual, is dual to each other. So the following will only consider the connected piece. Say the connected JT Euclidean path integral is a connected Riemann surface of n boundaries with beta 1 to beta n local lengths respectively. This computation can be factorized into this form. We can glue a trumpet for each beta and gluing all of them with so-called with Riemann surface bounded by n geodesics, and integrate over the geodesic length b using the measure b db. Okay, and we should integrate over the modular space of this geometrical object in the center. So that's corresponding to the Weil-Peterson volume. So this connected connected Euclidean path integral can be written in the form of this guy. Okay. Now we'll consider the generalization of this duality for GT plus n over brane To find the dual matrix model, the key is to find the inverse trumpet. Okay. The inverse trumpet is defined in this way. Okay, we integrate the trumpet against the inverse trumpet over the beta to get the measure of the end-of-warp-brane divided by B. Okay, why this is important? This just corresponding to that we can pinch off a trumpet and glue an end-of-warp-brane. For example, let's look at this. This guy is just some pure GAT computation of some geometry. We know that this is a trumpet gluing with rest geometry along the geodesic length B, right? And if we glue this guy with the inverse trumpet, and this guy will cancel with this guy, okay? So we'll get the rest geometry with this a measure of end-of-warp-brane, okay? So that's why we working in the Lorentzian canonical constellation to work out this measure of end-of-warp-brane. That is for us to find an algorithm to glue this measure to all the geometries, right? Okay. So for an end-of-warp-brane surface, we call it Zn. It can be computed by this Weil-Petersen volume gluing with the measure of the end-of-warp-brane for each of this geodesic loop and integrate over the B. Okay, and because of the inverse trumpet, we can rewrite it in the form of this one. Okay, all of these guys inverse trumpet just pinch off the trumpet and replace it by some measure. So this is a good formula. On the other hand, by this analogy, we can rewrite this Z into the expectation value of this trace of this trace E2 beta H operator with n products. Okay, so we get this guy. Now we can integrate each of this trace with the inverse trumpet respectively, and we can get this guy. Okay, so where the delta V I define in this way, and you can see easily that this is a minus trace delta V to nth power. Great. So now, if we have K flavor of the end-of-warp-branes, and we assume the indistinguishability for same flavor and sum over all the Zn, we can get the vacuum partition function with end-of-warp-brane loops. Okay, so this vacuum partition function basically corresponds to that, you consider closed surface, and you also consider, closed surface with one end-of-warp-brane loop, a closed surface with two end-of-warp-brane loop, and etc. Okay, and you sum all of them together, that should be the, vacuum partition function. So this guy is easy to sum, and you get this one. Okay, this is in the matrix model. You get you got a variation of the potential to the original matrix model. Great. Now let's talk about what is the Z2, the inverse trumpet. It is actually very easy to find. The trumpet can be inverse Laplace transformed, and the kernel is this one. Notice that this is a cosine function. Cosine function is very easy to invert, basically using this naive formula. So we can just write down that the delta V is just the cosine integrate over the measure. Okay. As before, this is divergent, right? Because when B goes to 0, this is divergent. Okay. This B go to 0 is infinity. Okay. And M the MB is also divergent when B is 0. Okay. But we can use zeta regularization to regularize this integration. The result is that we got, some divergent piece, a log gamma square term, and some constant term, and, some higher order terms. Okay. Notice that this divergent piece and this constant piece does not change the dynamics of the matrix model because it just shifts a constant term in the potential, which it can be absorbed into normalization. So in the end, we will get the effective change of the potential in the matrix model to be this minus log gamma square term. Okay, what does it look like? We can have a plot. So this is the curve of this delta V. Notice that because the gamma function, so it has some power. So the power is at this value, and this horizontal axis is the energy. So you see that, this is like constant like slope, right? So this extra potential will give you a left pointing force all the way to the left. Okay. So you can imagine if you have the spectrum of the GT gravity, this extra potential will pull the spectrum to the left. Okay. Now let's check the duality. We can compute, the partition function z beta on both sides. Z beta, z beta is just you have one ADS boundary and you glue whatever many loops of the underworld brains and genus together. Okay. On the gravity side, we have this guy, and this is just the symmetry factor. This is Weil-Petersen volume. This is the trumpet. This is the first trumpet. Okay, the beta trumpet, and this is Weil-Petersen volume, and this is some underworld brain measure. Integrate all over together. Here we only consider zero genus for simplicity, but we know that for the matrix model, if we already solved out the zero genus result and all higher genus result can be computed via the recursion relation. We will use a very non-trivial formula founded by Mertes and Turiassi of the Weil-Petersen volume, where it is the Bessa function and the U is defined in this way. Okay, those are, you don't need to worry about those details. In the end, you just use Lagrange inversion theorem, which is also computed using the same method by Maxfield and Turiassi, and to find the partition function to be this. And the 0 point energy is given by this formula, and where the F is this. Okay. Let me explain. Let me explain a little bit more. So the partition function give you first dependence of beta here, and has simply exponential beta times something. Okay. So you may regard this guy roughly as the spectrum of the system, although you have the different beta dependence here, right? So it's roughly. On the other hand, this zeta is determined by this very non-trivial transcendental equation, where the F is computed from the measure of underworld brain. So this is a sum in this form. Notice that this is also divergent, so this needs to be regularized. Later, I will just use a very naive regularization, just to add a cutoff here, and to see what will happen. So we can use the inverse Laplace transformation for the whole formula and get the density of state to be this. And so in this formula, the important thing is that there is a 0 point energy E now. Okay, the 0 point energy E now is determined by this equation. Okay, so let me roughly plot what it is. Okay, so if this is E now, then the rho basically go away like this. Okay, go away like this. So the whole integration gives you this plot, and the point is that to determine the E now affects the reflect the effect of the underworld brain. Okay, and there are a few interesting features. First of all, this function as a plot of E now, it is this. So it has oscillation like this. Okay, so it depends on the value of the second term. We will get a different value of the E now. For example, if the second term equal to this line, then the E now is this intersection. But if this value is this line, so the intersection here defines the E now. Okay. Actually, this is a regular E now, but this is a critical E now, because you can imagine if I have a lower plot, I will have a jump to this point, right? But later I will tell you that this jump is actually unphysical. Let me give you a few remarks. First of all, the F prime showing up in this formula is finite. but the F needs regularization. Let's assume it has a hard cutoff. Then we can see some interesting feature. First of all, when the E is near E now, the rho is E2 minus E now to 1/2 power. This is universal. For k equal to 0, which means no end-over brane, the E now is 0. So the density of state becomes JT gravity. You got a cinch and start the spectrum from zero. Okay, so this is the rho JT from 0. But for small k, you will shift the 0 point energy to left, right? You will get some negative energy 0 point, and you will get the change of density in the order of k. There exists a critical k, such that as the critical k, the density is this, is E2 E now to 3/2 power. So this is a plot. Okay, for ordinary k, you will get this plot. But for critical k, you will get this plot. But now after you're raising the k over the critical point, you will get this plot. You will get, because you get a jump of the 0 point energy, and you can show that it goes to like this. This is actually unphysical because you should not have a negative density of a state. Okay, so basically this means that there should be some phase transition. Okay, because time being, I just say one line that because on the matrix model side, because we already have the, a new variation of the potential, right? And we can use the conventional method in matrix model to solve out this density rho, and it turns out to be perfectly matched with this, gravitational computation. Okay, and also had this critical k and possible phase transition. So let me go to the discussion part. I mentioned many times about the regularization, but I did not really specify a very preferred regularization, because first, the regularization choice will affect the F for small k, but generally does not change the asymptotic behavior. So the asymptotic behavior, no matter what regularization you use, is always e to some number like a square root of e. This is dedicated by the ADS asymptotic symmetry. Okay, for large E, this spectrum is unchanged. So what is really changed is IR physics of the system. Okay, and this IR physics is actually quite dependent on the bulk UV regulation. Okay, so this is the IR UV connection from the other point, the second point from another point of view. And different regularization in particular will affect how the phase transition goes. Okay, sometimes at the critical point you will transition to type A. Sometimes you will transition to another type. That depends on the details of regularization. But maybe we can categorize it into a few cases and discuss the general cases of the regularization, general cases of phase transition. Yeah, this is work we are still working on. And if we take the most naive regularization, which is the hard cutoff, or the category of the regulation of it, then the phase transition will require a non-perturbative completion of the matrix model, which is beyond the scope of gravitational and geometric computation. So the point is that the matrix model dual JT gravity will give us a non-perturbative completion of the whole theory, and may give us, some especially some physics beyond the critical point, and some interesting physics may be there. So the non-perturbative completion, basically, okay, because of time being, let me just very quickly say what it is. The idea is the following. So we can look at the effective potential of the JT gravity, and we can find that though the support of the JT gravity is from 0 to infinity, but if we look at the effective potential, it has oscillation in the negative axis, and there are many regions with even lower potential than the eigenvalue lying on. This basically means that this matrix model is not integrating the eigenvalues along the real axis. Otherwise, the system should have found itself in the lowest energy, and all the eigenvalues should not be here. Should be somewhere here, and even more. Okay, so actually this means that this is a non-perturbative instability of this matrix model. So to avoid this one, we have to use a complex contour for each eigenvalue. Say, for example, this one and this one, rather than we integrate over along the real axis. Now, using this contours, we have basically two choices, one this as the other one for each eigenvalue. So you see here different choices of assignment of the eigenvalue on one of these two contour will give us different physics. Okay, so but all of these contour choices will give us complex eigenvalues in the spectrum. So the question will immediately becomes, okay, what is the most physical relevant or reasonable choice of the UV completion? What is the interpretation of these complex eigenvalues? And the last question would be more interesting, like, okay, we know that in the replica wormhole computation of a page curve, the phase transition occurs for large enough k, which is ordered as E2S now, okay? And in this matrix model, we see similar critical value of k, which is the same order as E2S now, in which we'll have possible phase transition, but a non-perturbativity. Is this phase transition related to the one? Are these two phase transitions are related to each other? Is actually an interesting question we are still working on. Thank you.
Thank you. Is there any question from the audience? If not, let me ask a question about the phase transitions, where you mentioned that you have some possibility of categorizing the different phase transitions depending on your choice of regularizations. Can you say more about that? It seems a bit strange that the physics sort of depends on the mathematical techniques we choose to regularize it, right?
Yeah. So this, it's a very good question. Typically, we may say, oh, the phase transition may be somehow universal in some sense, right? But here it shows the phase transition happens in the IR on the boundary, okay? But interestingly, that this IR physics on the boundary by the duality is corresponding to the UV completion of the bulk geometry, corresponding to the small b behavior,
right.
How we regularize it. So this basically means that if we have different UV completion, then we may have a different IR physics for this matrix model. Then it can have different phase transition. Okay, so you may ask, what is physical scenario or what is strong coupling system this may apply to? I think this is a good question, and I'm not quite sure now. Yeah, but I can tell you a little bit more about possible phase transition. For example. This is the critical point, right? Sometimes we may have this kind of phase transition. We may have, for some choices of regularization or correspond to the matrix, we can have this and this support. Okay, so this is the one support of the spectrum. This is the conjugate support spectrum. This means that all the eigenvalues become complex. Okay, so the complex eigenvalue of the system may correspond to, say, resonance state of the black hole. Maybe which means that the black hole becomes unstable in some sense. But we are still trying to understand in more details. For example, we can also choose some other regularization to get this shape of the support. Okay, the Y shape. So this shape of support. Oh, so this is in the complex plane. Okay, this is support of the spectrum. So you can have some piece to be complex value, some piece of complex value, but you can still have some real eigenvalues, real energies in the spectrum. So this is possible, another possible category, and there are some more. Yeah, but we're basically figuring out a few types.
Okay.
Yeah.
Is there any other question from the audience?
I have a question. Hi, Ping. Nice talk first. So I have a question maybe related to the previous one. When you say phase transitions, do you mean a phase transition within one UV completion, or you are saying that different UV completions give you different phases?
Oh, yeah. Different UV completion give you different phase transition.
Okay, but then why as a transition? Because usually I will think of like you have a UV completion and then you just stay in this one single theory. But you go from UV to IR. There's no more. You don't change from one UV to different UV.
Oh no. So this is I think this is not okay. Well, okay. So I think this is not okay. So first of all, how the phase transition? Yeah, maybe the word phase transition is not that improper. Here I phase transition refer to the parameter K. K is the flavor of the endophore brane. Right. So if we're saying, okay, give you a theory, fix a theory with UV completion, of course you fix a number of the endophore brane, then that is the theory itself. There's no phase transition because we need to tune the K to get the different phase. So here the order parameter is not the temperature for them, but it is the K, the number of endophore brane.
Okay.
Yeah, so it's not like you give your theory, you flow to different phase. Yeah, it's not like that. Yeah, if you regard the K also defining different theory. Yeah, maybe. So. Yeah, but I would say this is like a phase transition of a matrix model, because from matrix point of view, the K is just a parameter. He has no idea about what is the geometric meaning of K is, right? So from a matrix point of view, it's just a phase transition, and the K is a parameter.
Right. I see.
Yeah,
I see. So okay, and also this seems to suggest that for the same IR physics, there could be different UV completions.
Yeah, exactly. Well, for the same IR physics, maybe, yeah, okay. I would say different. Maybe there are different categories, right? Okay, some IR physics they make. Okay, I would say same type of UV completion may correspond to universality of the IR phase. Yeah. But if you change the UV completion quite a lot, then the IR will be different. Yeah.
Okay. Yeah. Thank you.
All right. Any more questions? If not, we'll end the morning session. Thank you, Yingao.
Okay. Thank you.
Thank you. Yeah, the afternoon session will start from 2 p.m. I'll just leave the room.